Good afternoon, Professor Biji. So, can we start the presentation? Okay. So, I am Subramanian. Let me introduce you, and then you can share the presentation. Friends, in this session, Professor Biji, Professor in Nanotechnology, PSGIAS Institute of Advanced Studies, Coimbatore. She is going to deliver the talk. And she obtained PhD from IIT Madras and MSc from Cochin University. Her career spans over a decade, progressing from assistant professor to her current professor position in nanotechnology. She specializes in gas and ion selective sensors, self-cleaning coatings, clean energy materials. As the head of the Department of Chemistry and Nanoscience at PSGIAS, she is a recognized leader. Her achievements includes a number of awards, grants, patents, publications, and she has also gained a number of PhD students. And she has substantially contributed to the field. Over to Professor Biji.
So, good afternoon all. So, thanks for the nice introduction. And I'm extremely happy to be part of this Energy Summit and to deliver this talk. And thanks to the organizers of Energy Summit, and a special thanks to Dr. Raman for giving me an opportunity for this talk. So I come from PSGIAS Institute of Advanced Studies, Coimbatore. So this is the Nanotechnology Research Center located in the PSG College of Technology, Pilamedu. So energy is one of our major thrust area of the research. So more about our activities, I request your attention to our website, psgias.ac.in. Today I will be speaking about some small work on what we did on proton exchange membrane fuel cells. Of course, Dr. Raman Vedarajan from ARCA have given a nice overview about proton exchange membrane fuel cells and various aspects of that. So my job is little bit easy in that line, especially in the introduction part. So I will be talking about a little bit different in the material perspective. So I would like to talk about the surface engineering on Mesoporous Carbon Nanofibers, which can be used as a potential electrocatalyst support materials for boosting the performance as well as the durability of proton exchange membrane fuel cells. So these are preliminary things, what I'm just starting about. But as all of you know that IC engines, so we are getting approximately 30% of effective power only from 100% of fuel efficiency. However, in fuel cells, the theoretical efficiency is calculated to be 83%. But due to various losses, we try to get experimental efficiency somewhere around 50 to 60% of practical efficiency we can acquire from fuel cells. Since we are using hydrogen as a fuel, what we are getting, what we are doing in a fuel cell is a direct conversion of chemical energy into useful electrical energy, which can be used for our energy demand purposes. So fuel cells basically produce, as all of you know, that clean energy with a zero or very low emissions. And another advantage is no moving parts. So therefore, we can require, it doesn't require any maintenance cost, or we can also reduce the life cycle cost for the energy production. So Dr. Raman also mentioned the various applications of PEM fuel cells. It has various applications in transport applications, stationary applications, as well as portable applications. But it has advanced a lot in the case of transport applications. Most of the automobile corporates have already launched their products, and some of their cars are running in various countries. And there are some fuel cell buses, fuel cell trains, and recently NTPC has launched a fuel cell buses in India. And recently we also have seen some news like the fuel cell powered aircraft has made its test runs. So although there are there are many attempts to move forward in terms of commercialization of fuel cells, but major obstacles are coming from the cost, high cost and the durability. So as Dr. Raman mentioned, if you see the cost breakup, the major cost contributor is the electrode itself. Approximately 51% of cost is coming from the electrodes, which is constituted by the membrane and of course the electrocatalyst. So electrocatalyst typically in a fuel cell what we are using is platinum based electrocatalyst. So therefore the cost is going to be high. And other major contributor is bipolar plates. This is mainly fabricated by graphite plates or in some cases stainless steel. So if we are able to bring down the cost of the electrocatalyst and the bipolar plates and other components, we can typically reduce the manufacturing cost of PEM fuel cells. And Department of Energy also used to introduce the future targets. So if you see 2005, the cost per kilowatt was approximately $125. So lots of progresses have been happened in this line over a period of a few decades, last few decades. So now we are somewhere around $40 per kilowatts. We could bring down the cost by reducing the platinum loading as well. So India also has our own targets. So our targets are divided into 3 phases. The first phase started somewhere around 2016. So we try to develop fuel cells of a few kilowatts at a cost of 2.5 lakhs per kilowatts with 30% imported components. However, in phase 2, target was to manufacture fuel cells to the cost of 2.5 lakhs per kilowatt with 100% indigenous components. Third phase target was to reduce the cost to 50,000 per kilowatt. So you already have heard from Dr. Raman about the fuel cell working principle. So I don't have to spend much time on this. So it's just opposite to what we are doing in water electrolysis. So in this case, at the anode side, we are splitting hydrogen into protons and 2 electrons. Basically, the hydrogen oxidation reaction will happen at the anode side. And the whatever protons which have been formed will move across the proton exchange membrane to the cathode side, and the electrons will be moving through the external circuit to the cathode side. And at the cathode, we are feeding oxygen. So the protons will react with the oxygen, and water will be formed as a product. So along with that, what we are getting is electricity and a little bit of heat as a byproduct. So now, if you see this expanded view of the design of a single fuel cell, so we already know that MEA is the heart of fuel cell, in which the proton exchange membrane is sandwiched between the cathode and anode, which will be eventually assembled with the gas diffusion layer and the bipolar plates and so on. So basically this whatever oxygen reduction reaction which is happening is a sluggish process. It's a difficult task. So we have to use lots of electrocatalyst at the cathode side basically. So if you are following a 4 electron pathway, then the job is a little bit favorable. In some cases, we can also see that it follows the 2 electron pathway. So now, if you see closely the membrane electrode assembly, as I told, it is the membrane is constituted by a proton exchange membrane, which is sandwiched between the cathode layer and the anode layer, as shown in this figure. So if you see the catalyst layer, what we have to mainly look into is like generally what we do, material scientists will look into improve or increase the surface area, and therefore the properties will be enhanced. But in this case, if you are if you are designing a catalyst layer. So what we have to look into is not to increase just the surface area. What we have to increase is the triple phase boundaries. So what are these triple phase boundaries? So these are the interfaces where the electrolyte, gas, and the electrically connected catalyst agents should be in contact. So this kind of active sites should be increased instead of just increasing the surface area. So this is applicable to both sides, both anode side as well as the cathode side, where hydrogen oxidation or oxygen reduction reaction will be occurring. So we have to basically we have to basically understand that we have to improve the triple phase boundaries. So now let me come to one of the material what we are using in the catalyst layers. So I don't want to talk about the electrocatalyst. Platinum is the best electrocatalyst ever known. We know about it, and there are many advancements have happened in that field, like platinum alloys and many other binary, ternary, that kind of electrocatalyst. And some cases, many researchers have are working on a non-noble platinum-free electrocatalyst as well. So that's a big area. So I don't want to discuss on that line. So what I am looking for is support material. So the best support material or the most popular support material which are used in proton exchange membrane fuel cell is carbon-based material. So the role of support material is one is that you should have sufficient specific surface area. So the method of preparation is very important. And secondly, the metal support interaction should be sufficiently good. And another important prerequisite is that it should be electrically conductive to be used in this kind of fuel cell or battery applications. So, so basically, it will try to improve the uniform composition of the electrocatalyst nanoparticles on the catalyst layer, and of course the major role is the electronic conductive pathway. So it will provide a means to transport the electrons into and out of the catalyst. And one way to improve the properties is to dope some foreign elements like nitrogen, sulfur, boron, or phosphorus. So this kind of heteroatom doping will assist or aid in improving the properties of support material, especially the durability as well as the uniform deposition of the electrocatalyst. It also will improve the active sites with the three-phase boundaries. So there are many carbon-based support materials that are already commercialized, like a Vulcan carbon, Kitchen black. So in India nowadays we are trying to use this kind of a commercial carbon-based support materials, but of course its properties has to be improved further. So nowadays there are many other type of carbon materials also have been used, like carbon nanofibers, carbon nanotubes, graphene, and all. And there are some non-carbon support materials also have been used, like titanium nitride, metal oxides, transition metal carbides, and all. So we have to effectively increase the specific surface area conductivity as well as electrical conductivity. So another important criteria is that to introduce mesoporosity into this kind of support materials. However, we have to understand that if we are able to provide or introduce porosity in like easily accessible porosity, if we are able to introduce into this kind of carbon support materials, we can improve both kinetics as well as the transport properties in the catalyst layer. So although there are many advantages of carbon, like high electrical conductivity, and we can get high or a large electrochemical surface area and the good chemical stability, but there are some inherent issues also with this kind of materials, like carbon corrosion. So that is one of the serious disadvantage of carbon-based materials. So this carbon corrosion basically it happens due to the oxidative corrosion of carbon. So carbon in various forms, we know that it is thermodynamically stable below 0.2 volts and kinetically stable above that potential, which means that above this potential it will become thermodynamically unstable and will try to undergo oxidation. So this oxidation of carbon will happen. It will react with water and forming carbon dioxide, either carbon dioxide or carbon monoxide. So that is one disadvantage, and it will eventually end up in issues like platinum dissolution from the support materials and oswald ripening, agglomeration, and all. And in some cases, this electrocatalyst particles itself will detach from the support materials due to carbon corrosion. So this will generally occur because of due to local fuel starvation or the startup shutdown cycles or cell reversal processes. So our strategy to design the materials for the carbon-based support materials at PSGIAS is like we try to develop or design our materials with less platinum electrocatalyst, which means that we try to produce a uniform distribution, approximately 2 to 3 nanometer platinum particles. We will try to distribute throughout these support materials. And we are also involved in producing less platinum bimetallic electrocatalyst. So in that way, we try to increase the effective utilization of platinum electrocatalyst and reduce the platinum loading. And secondly, we focus on introduction of mesoporosity, intentional introduction of the mesoporosity into carbon support materials. So this we do using electrospinning. So I will explain to you how we are doing in the next forthcoming slides. So we try to introduce some porogens, and then we produce mesoporous carbon nanofibers. And of course, with our methodology, we create abundant endo active sites. So these are basically originated from the inherent endo sites, carbon nanofibers, since we are using polyacrylonitrile. And of course, we are also trying to introduce abundant endo active sites by deposition of the surface layer of the graphitic nitride or titanium nitride on the surface of carbon nanofibers. So coming to the methodology, what we are adopting. So we have specifically formulated one methodology to create intentionally induced mesoporosity into carbon nanofibers using electrospinning. So in electrospinning, we try to force this polymer solution through the conductive needles, and this is connected to a high voltage source. And then because of this high voltage, this polymer fibers will try to split into nanofiber structures. So to introduce mesoporosity, what we did, we used the precursors as polyacrylonitrile, and we tried to introduce ball milled sodium bicarbonate nanoparticles of the size of the 2 to 50 nanometer size range. So we try to blend this sodium bicarbonate nanoparticles into polyacrylonitrile solution, and we use that as a feed solution for electrospinning. And further, what we did, we tried to stabilize this polymer nanofibers at a 300 degrees Celsius under oxygen environment, and followed by carbonization. To remove the sodium bicarbonate, we attempted carbonization at 800 degrees Celsius in the nitrogen atmosphere. So during this process, we could understand that thermal decomposition of sodium bicarbonate was observed, and further we tried to do water washing, so that entire sodium hydroxide, whatever has been formed, was removed, leaving the mesopores on the surface of the carbon nanofibers. So effectively, what is going on during the stabilization process in air? Dehydrogenation and the cyclization of the polypan fibers will happen, and followed by graphitization process in an inert atmosphere. So during this process, initially dehydrogenation followed by denitrogenation will happen, and then some graphitic domains will be formed with some endopsites. So these are some of the HRTM analysis and then scanning electron microscopic analysis. So you can see nice mesoporous structures have been formed throughout these carbon nanofibers, and you can also see the same in SCM analysis also. And now further we try to introduce the platinum electrocatalyst on the surface of Mesoporous Carbon Nanofibers. So for this, before reducing this platinum, what we did, we tried to do some functionalization process, which created so much of active regions on the Mesoporous Carbon Nanofibers. So this was followed by ethylene glycol reduction. We can also attempt a photo reduction and many other reduction processes for this purpose. So with that, we could understand that this process ended up in a very nice uniform decoration of 2 to 3 nanometer sized platinum nanoparticles throughout this mesoporous carbon nanofibers. Very uniform decoration over this surface. So this itself will indicate that the performance will be better than the commercial electrocatalyst. So for that, we also try to do all material characterization, and then further we have to prove that it is electrochemically active. So for that, we performed cyclic voltammetric electrochemical analysis, like cyclic voltammetry. So initially we tried to evaluate electrochemical surface area. So for this, we used CV in nitrogen saturated sulfuric acid solution. So we could observe the nice hydrogen adsorption and desorption peaks, and then from that we try to derive this electrochemical surface area from the adsorption hydrogen adsorption peak using this formula, and we understood that for mesoporous carbon nanofibers, the electrochemical surface area was around 95.3 meter square per gram, which was almost like a double to the commercial PTC. And further we did this ORR performance of the materials and compared with the commercial PTC also in oxygen saturated sulfuric acid solution. So we could see that this ORR performance has been increased considerably compared to the commercial PTC. And we extended this study on ORR using linear sweep voltammetry using rotating disc electrode at 1600 RPM. So eventually we can see that this onset potential and half-wave potential has been shifted more positive in the case of mesoporous carbon nanofibers compared to commercial PTC. And we also could see that the current density, limiting current density, has been increased in the case of this mesoporous carbon nanofibers. And to understand the ORR kinetics and electron transfer number, again we conducted this LSV under different rotation rates using RDE. So we also attempted this KL plots to understand to calculate the electron transfer number using KL equation. So we could see nice linearity and parallelism, and from this slope and intercept we tried to calculate the electron transfer number, and it was found to be approximately 4. So that indicated that the reaction pathway of ORR in acidic solution was following a 4 electron pathway. And further we studied the stability of the materials using chronoamperometry accelerated durability testing. And initially chronoamperometric studies have indicated that the current density was retained to the order of 89.8% in the case of mesoporous carbon nanofibers, while PTC was degraded faster over a period of 30,000 seconds, and it was found to be approximately 65.2 in the case of a commercial PTC. So there was a considerable increase in the stability was observed. And further, before and after ADT test, after 10,000 cycles, we tried to measure this LSV plots, and then it was observed that there was a smaller shift for the PT mesoporous carbon nanofibers. But if you see the commercial PTC, the shift was much higher. So it means that the degradation is much slower in the case of mesoporous carbon nanofibers. And after analyzing all the properties, then we attempted the fabrication of MEA. We did the MEA fabrication, and then further single cell assembly was done, and then the polarization curves were measured, and then we could see that the power maximum power density obtained for the Mesoporous carbon nanofibers was somewhere around 428 milliwatts per centimeter square. It was almost like a double to the performance of the commercial PTC. The current density also was following the similar trend. So, which means that the usage of mesoporous carbon nanofibers could effectively improve the performance of proton exchange membrane fuel cells. So, this is basically we understand that there are many factors in that, but of course, the introduction of this endowed size and the mesoporous structure and the uniform deposition of platinum nanoparticles have effectively contributed towards enhancement of the performance. So similarly, we also try to do a different kind of material, like we try to do hollow carbon nanofibers using the same method, electrospinning. But in this case, we used coaxial electrospinning. So we used sacrificial polymer as a core material, which like a PMMA, and same process like carbonization and stabilization followed by carbonization process was attempted. So in that case, PMMA was decomposed off and leaving a hollow structure inside the carbon nanofibers. So the same process only we attempted. So we could get this mesoporous structure again with the hollow carbon nanofibers, and effectively we could improve the kind of distribution of platinum electrocatalyst on the surface of these carbon nanofibers. So this material also could improve the performance almost in a similar trend. Not much of variation compared to the normal mesoporous carbon nanofibers. So to conclude, we understand that instead of increasing just the surface area, we should focus on improving the triple phase boundary sites, which should play a major role in to improve the performance of PEM fuel cells. So in our case, in the case of the mesoporous carbon nanofibers, the overall enhancement in triple phase boundaries was achieved through amalgamation of some of the characteristics like high specific surface area, introduction of mesoporosity, and of course the presence of endowed sites like a pyridinic, pyrrolic, and the graphitic nitride kind of nitrogen species was introduced into this, and all these characteristics have aided in uniform distribution and optimal size platinum nanocatalysts over the surface mesoporous carbon nanofibers. So this material can be used as a potential alternative for conventional carbon support in PEM fuel cells. So our idea is like hydrogen, if we are producing from a renewable or green source. So if you are coupling with a fuel cell generation on demand, that can provide a sustainable solution for energy conversion. So I would like to thank my group. This is my group, and Professor Manoj from PSGIAS. So he helps us to assemble the single cell as well as the PEM fuel cell stack and system assembly. And my group is basically working on the materials and the characterization aspects. And I would like to thank our funding agencies. So initially, PST Institute of Advanced Studies was investing on this fuel cell research in our institute to create basic infrastructure like electrochemical workstation and all. Further, we received a grant from DSTHFC. So with that, we try to develop a durable mesoporous carbon nanofibers. So our idea was a little bit different. So after creating this mesoporous carbon nanofibers, we tried to deposit anti-corrosive layers like a titanium nitride on the surface of mesoporous carbon nanofibers, which could effectively improve the durability of the layers. And recently we have received a good grant from Center for High Technology, Ministry of Petroleum and Natural Gas. So that is in collaboration with BPCL, and we are trying to develop fuel cell stack of 2.5 kilowatts using that project. So thank you for your attention, and
thank you, Professor Biji, for the wonderful talk. Hope you will take few questions from the audience.
Yes, please.
Thank you, ma'am. I am a student from the University of Sydney. I am working on PhD. I just wanted to know what would be the what would be the rate limiting step in the part.
It's not audible properly. Can you be louder?
What would be the rate limiting step during this pathway when you introduce force?
Basically, what we have observed is that our electrochemical pathway was following a 4-electron pathway. So that actually we have to take care of that aspect. So we have to do this LSV experiments using a rotating this electrode, and then we can understand what mechanism it is following. So if it is going to be a 2-electron pathway, then the reaction rate is going to be limited.
Is there a possibility that even during 4-electron pathway, the formation of peroxide happens in a fuel cell? So how do we control that? How do we control the formation of peroxide?
How do we control the
formation of peroxide during the pathway?
Yeah. Peroxides generally will form if it is following a 2-electron pathway. So in the case of a 4-electron pathway, it doesn't form much of a peroxide radicals.
Even the meager amount that is being formed, how do we control that is my question.
Hello?
Yeah, thank you for the clarifications. Any other question? Yeah, Dr. Raman has some questions.
Yes, sir.
Professor, it was a wonderful presentation.
Yes, sir.
So I have, it's out of this presentation, are you also working on modifying the gas diffusion layer, because you show that you are working on fibers from PAN?
Yeah. Actually, currently we are not involved in that aspect, but however, we can look into, because electrospinning is a versatile technology to produce mass production of carbon nanofibers can be done. So we can also attempt a gas diffusion layers later on. So, but currently we are not working on it.
Because the technique shows that you have that ability to make a single brick.
Yes. We can make very good electrospin mats as well.
My second question is on were you able to control the amount of platinum loading precisely onto the CNTs?
Yeah. So what we do is we compare our materials properties with 20 weight percentage commercial PTC. So we try to use the same amount of platinum, like a 20 weight percentage platinum only for our preparation of our electrocatalyst support materials, so that we will not end up in more utilization of more platinum into this. So, but effectively with the same platinum loading, we are getting almost like a double, twice the performance compared to commercial PTC.
Because the major bottleneck which I see is dispersion of 20% platinum on CNTs to be the determining step for your material. But since you have got a very good material, I think it's wonderful to showcase it. Second, the third point is you showed about ADT. Also, there are some protocols by Ballard which shows usage of triangular waves, pulse waves, to measure the emission rate of carbon. If you can adapt those protocols also, your
sure,
will go up.
Yeah, sure. And again, this MA, yes, MA stability also currently we are doing. So, yeah.
Thank you so much.
Thank you. Thank you, sir.
Thank you, Professor Biji, for giving this wonderful talk and joining through online, taking pain.
Yeah, thank you.
Hope to have you here sometime. Right.
Yes, sir. Yes, sir. I would like
the
to.
excellent
Yeah.
presentation. Thank you.
Thank you, sir. Thank you.
Thank you. Probably conveners will send all the details to you. Memento or whatever it is.
Yeah, sir. Thank you. Thank you so much. Yeah.